So we are set, ready to go for the afternoon talk. It's a pleasure to have Lorenzo Mai here from Sussex University, and he'll tell us about electroweak logarithms and open loops. Please.
Thank you very much, and thank you to the organizers for this opportunity to present my work in collaboration with Jonas Linder today, this workshop. So, in the spirit of efficient automation for the evaluation of higher order correction, we developed and implemented in OpenLoops an algorithm to evaluate one-loop electroweak pseudocode logarithms, which, as of course now, are the dominant contribution of electroweak relative correction in the high energy regime. I will limit myself today at next to leading order level of accuracy, which is the current level of approximation of our implementation, where we have to deal with both double and single logarithmic terms, okay, involving the ratio of the energy over a given reference mass scale. Due to this dependence, such logarithms can significantly enhance states of kinematic distribution up to several tens%, as it has already been shown in previous implementation, also in Davde's talk yesterday. And of course, it has already been shown in the original work of Nenner and Ponzorini of 2001, who for the first time developed an algorithm, the DP algorithm, to properly derive and evaluate such next to leading order correction at one loop. This algorithm is based on the logarithmic approximation, which roughly speaking consists in these couple of points. So in working with energies and invariants built with the external momenta for a given process, which are always of the same size and much above all possible masses entering in the game. And from the one loop correction, neglecting all constant and mass suppressed terms relative to the leading order matrix element, keeping only the dominant contribution, which are indeed the double and single logarithmic terms. Now, before entering in the details of our implementation in OpenLoops, let me quickly review how such logarithms, double and single logs, arise at NLO level, starting in particular from double logs. So, double logs come from the exchange of a soft and collinear gauge boson B between two external states. And if one employs the Apollon approximation to extract the double logarithmic structure from this loop integral, it will be possible to recast such loop integral in a very easy scalar three-point function, the C0, which in the loop amplitude turns out to factorize. So in other words, the loop amplitude for such diagram will be something like power of alpha, decoupling of B to the external states, the C0 evaluated in the logarithmic approximation, which is factorized, and everything multiplies the leading order matrix element of the corresponding process. Here RKL is our notation for the invariant built with the momenta of the external K and L particle. Due to this factorization, we have that pseudocode logarithms are then universal, and this general structure can be then tested in a totally process-independent way, as long as, of course, we satisfy the condition of the Denner-Pozzarini algorithm. And of course, this universality is preserved if we employ standard mathematical properties of logarithms, which each of us has learned during the high school. And so then it's possible to have universal logarithms split into three subspecies, which are called here as leading, subleading, and sub-subleadings of collinear. So the names, the part of the name that is said to be soft collinear is just a way to have a remnant of the origin of such double logs, which is, again, when a soft and collinear gauge boson B is exchanged between two external states. Leading, subleading, sub-subleading is a sort of way to have in mind the hierarchy among all of them, even though in the original work of Denner-Pozzarini, this sub-subleading was not called like that, so it was just named by us in this way, and also because it was neglected. As you can see, indeed, it depends on the log square. It's basically the log square of RKL over S, and if we are in the pseudocode regime, being RKL always of the same size of S, this is in principle negligible, okay? Then, of course, being the subleading dependent on, again, the log of RKL over S, this contribution will be sub-leading compared to the biggest in principle one, which is the leading soft collinear. The difference between them is just that while the leading soft collinear is totally angular independent, and it factorizes in a very easy way as a single sum over the external states, subleading and sub-subleading, having the dependence on RKL, are factorized as a double sum over the external particles. However, as we will see later in some results that have been obtained with our implementation, there are observables in which the Sudakov regime is not preserved, is violated. And this is the reason why there are a hierarchy among invariants, which are the responsible of having non-negligible sub-subleading contribution, and sometimes a sub-leading one as sizable as the leading soft collinear. But this will be even more clear later on. So let me move on to the single logs, which in general have a triple origin. They can come from the UV renormalization of electroweak dimensionless parameters and from the renormalization of the external fields, where again, if one employs the logarithmic approximation, it will be possible to find the next to leading order correction, which is factorized as the leading order matrix element multiplied by a correction factor delta that contains our additional power of alpha, because we are next to leading order, and the logarithms. However, as I said, there is, yes, of course, we don't take into account renormalization of masses and of couplings with mass dimension, because for the same reason that I said at the beginning, they give rise to mass suppressed contribution, and of course, they are not always also universal. So they are totally neglected in our implementation, as well as in the original Danner-Pozzini algorithm. Okay, as I said, there is a first source of single logs, that is the external lag emission of a collinear, gauge boson B. And again, if one employs the icon approximation and extract the single logarithmic term from the loop integral, it will be possible to find a factorized amplitude as Bohr matrix element times algebraic factor delta, which contains the log and the additional power of alpha. Now, since this last contribution and the previous one from wave function renormalization are both associated to external fields, they are usually summed together and one study this full gauge invariant result, single logarithmic correction for external fields, labeled as C. Also in my plots later, I will show you C rather than collinear and wave function separately. Okay, this concludes the very concise review of how Sudakov logarithms arise in next to leading order. And let me now describe a little bit something about our implementation. And I know that I can imagine that some of you may wonder, okay, but next to leading order, electroweak correction have been almost basically fully automated nowadays, and Sudakov logarithms are already implemented in different frameworks. So what's the real purpose to implement them also in OpenLoops? Well, I asked it also to myself some time ago, and well, the point is that actually, even if you automate next to leading order correction, and we know how to do them, they can be complicated, in particular if you increase the multiplicity for in a given process. And this clearly gets worse if you go to NNLO to loop in general, where there is no full automation at the moment. On the other side, at least the electroweak Sudakov logarithms have two very nice properties. They can, in principle, approximate the full NLO result, being the dominant contribution, and they can be associated to external states only because of the universality. So the idea was to use this couple of features to implement in OpenLoops an algorithm. If you don't know what OpenLoops is, it's not the purpose of this talk. Just think about it as a matrix element generator to evaluate 3 and 1 loop amplitudes. And we, as I said, develop and implement in OpenLoops an algorithm to compute such next to leading order correction, but with 3 topologies only, which of course, because you don't have to compute the loop anymore with the analytical results that I showed you before. And this, of course, is a clear benefit in terms of time evaluation. So how did we do it? Well, we simply took a general V5 prime electroweak vertex, where V is a gauge boson, 5 prime, whatever standard model fields associated, allowed by the electroweak Feynman rules. And we constructed a corresponding 5 prime effective counter-term vertex. This vertex has the same rule, EI and capital I, the Feynman rule of the original vertex, but with this additional function K that contains the logarithmic structure. Then, what do we do with this set of rules? We don't construct anymore, for example, let's take the Drellian process. We don't construct anymore a given loop diagram, okay? We construct the corresponding tree diagram with this counter term, effective counter term insertion on the legs that would have exchanged the gauge boson B. And by default, with this set of rules, this diagram on the right has an amplitude M, which is the leading order one due to this part of the diagram, times the additional power of alpha here, the couplings of B to the external states, and the logarithmic structure. This is exactly the factorized form that we have seen many times before for all the Sudakov contribution. And this is exactly what you would get from this diagram if we evaluate it in the high energy regime. The difference is that you get the same result without computing the loop. So this, of course, as I said, requires much less time for the evaluation. This is the way in which we evaluate collinear and soft collinear Sudakov corrections, but not the PR. For the PR, I didn't show you before the same factorization of all the other contributions, simply because the single logarithms, Sudakov logarithms from PR, come from the running of the electroweak dimensionless parameters from the renormalization scale to up to S, okay? But nevertheless, they are still single logs, they are still universal. And the way in which we decided to evaluate them was just to, since OpenLoops is thought to evaluate one loop amplitudes, so full one loop amplitudes UV finite, to use the standard UV counter terms already implemented in OpenLoops, simply setting the wave function correction to 0, because we decided to evaluate with double counter term insertion on the external fields. However, in our code, it's also possible to keep the wave function correction in the standard UV counter term and simply setting the wave function correction from external fields for double counter term insertion to 0. Otherwise, there would be a double counting of this single logarithmic contribution. Okay, that was just a way for us to cross-check the results and to debug. But in principle, it can be done in both ways. Okay, I can now show you some results that have been obtained once then we interface OpenLoops with Sherpa. And I want to start from this PT distribution of the hardest vector boson in WWZ production at 13 TeV. Now, in the left plot, you can see the each Sudakov contribution, basically leading, subleading, sub-subleading, and so on and so forth. And as you can see, the dominant contribution is the leading soft collinear. Subleading is a little bit smaller in magnitude, and the sub-subleading is, as expected in the Sudakov condition, very, very small. On contrary, on the right plot, you can see the comparison of our two NLL approximations, NLL and NLL prime, against the full NLOVI result, so the pure virtual correction infrared subtracted. And the difference between green and red distribution is just this yellow distribution here, the sub-subleading. So while the red is the sum of all of them, the green distribution is missing the sub-subleading. The reason to show such difference will be even more clear with the next plot, which is the total invariant mass of the system. So here you can see that subleading and sub-subleading are not so small anymore. Subleading is even bigger than leading soft collinear, and sub-subleading is bigger than all the single logs, basically, okay? While in the previous case, it was smaller than both single logs. So what's happening here? Well, the reason is exactly what I said to you before in talking about double logs. Here there is a violation of this Sudakov regime. So we have a sort of hierarchy between invariants, which are not always of the same size of S now. And this causes the subleading and sub-subleading, which depends on the ratio of RKL over S, of the log of RKL over S, to be now very sizable and very, very big. The point is that now, if we don't include the sub-subleading, we get this totally wrong green distribution here. It's not really a problem in terms of magnitude. It's really a problem in terms of sign, if you notice, because it's totally, I mean, it's positive, okay? And on contrary, if we keep the sub-subleading, we recover perfectly the NLOVI result. So you may wonder, okay, but then just include it and you're done. You get a perfect agreement. Well, not really, because sub-subleading like terms actually come from also the logarithmic approximation in the energy limit of the box diagrams. So there is no full control on them. And even though they seem to be important and give rise to a better agreement with the full NLOVI result, they should be rather thought, we think they rather thought as a theoretical uncertainty of the approximation, okay? And indeed, it's not guaranteed that if you include them, you get a perfect agreement. And this is exactly a proof of it, because this is the invariant mass distribution of ZZ in ZZ production, again, at 13 TeV. Here, I mean, sub-subleading is as sizable as leading soft collinear, which you wouldn't expect in principle. And again, if we don't include sub-subleading, totally wrong. It's a disaster, this approximation. But if you include it, at least you get the correct sign, but not the correct magnitude. This is exactly because there is no full control on sub-subleading-like terms. This is the PT distribution of the hardest Z boson. Here you can see sub-subleading is basically vanishing. So green and red distribution are overlapped, and they are also in a very nice agreement with the NLO result. So in this case, the approximation is remarkably good. As it is good, actually, again, if we treat sub-subleading like terms as a theoretical uncertainty to be kept into account, the PT distribution of the hardest top quark in TTW production, again, the agreement including it, it's quite remarkable, as well as for the invariant mass distribution of the whole system, again, in the same process. Okay, now I can summarize basically the Denner-Porcini algorithm in 2 points. And this algorithm tells us if you go at very high energies, the next to leading order rate correction are double and single logs, and they are universal. So you can evaluate them just via the external states only, okay? And this is true, okay? The point is that, what if I want to evaluate Sudakov correction for a process which is dominated by a resonant configuration, like, for example, PP into lepton, anti-lepton, and jet, where the lepton and anti-leptons come from the decay of a virtual Z boson. Well, the standard algorithm would simply evaluate the Sudakov correction associated to the quarks, and that's fine. But for any kinematic point, for any phase space region, it would evaluate the Sudakov correction on the lepton and anti-lepton, because as I said, it evaluates the correction for external states only, okay? But if the process itself is dominated by a resonance, so where the Z is nearly on shell, we don't want to evaluate the Sudakov correction on the leptons, but the Sudakov correction on the Z boson. So how can we overcome this problem? Well, with our counterterm approach, this insertion of effective counterterms, we simply decided to generate also diagrams with an insertion on the decaying particle, in addition to the diagrams with insertion on the decay products. We simply weight these kind of 2 different diagrams with different function, PZ and 1 minus PZ. This PZ has really the meaning of a projector. Why? Because, okay, this is a very non-fancy form for the P function for the projector, but because it involves the complex mass, the real mass, the width, and of course, the momentum of the decaying particle. But it is thought to go to 1 if we are nearly on shell, so that the Sudakov correction associated to the leptons are automatically set to 0, and we evaluate the Sudakov correction of the Z boson. Vice versa, when we are far off shell, we set to 0, the projector set to 0 these diagrams here, and evaluates correctly the Sudakov correction of the decay products. And with this approach of internal plus external, insertion, we have obtained the following plots for E plus, E minus plus jet. Now, let's focus for the moment on the plot on the left, which has been obtained for the lepton invariant mass between 75 and 107. So it is capturing really the resonance. And here, green and red distribution and LL and LL prime have the same meaning as before. So they differ just for the sub-subleading, but here it's not important if they are overlapped, because the sub-subleading is very, very small. But they have been obtained with this internal plus external approach. NLOVI is still the full NLO virtual and infrared subtracted electroweak correction. And the light blue distribution is the Sudakov correction with with our code, but with external insertion only. And lastly, the purple distribution is the Sudakov correction for the R process only, so for the on-shell Z plus Z. So you can see that if you employ just external insertion as the standard Dennett Pozzeni algorithm would do, you get a wrong prediction, a very nice behavior, but an error in terms of magnitude. As well as if you just compute the Sudakov correction to the R process only, because it's okay up to a certain point, but that there are off-shell effects that correct the correct results. On contrary, if you employ our approach with internal plus external, which dynamically, depending on the phase space point, sets the Sudakov correction for external or internal fields to 0, you can perfectly recover the NLOVR result. Here, however, on contrary, we are for a dilepton invariant mass far off shell between 2 and 500. So the purple distribution, of course, doesn't make sense anymore. And also, since we are far off shell, all the internal insertion are automatically set to 0. And this is why the light blue distribution and the red one are basically overlapped. And also in this case, in a very nice agreement with the NLOVR result. So in conclusion, I've tried to review today how Sudakov logarithms arise and next to leading order, weak Sudakov logarithms arise and next to leading order level of accuracy, and trying to stress the main point, their main feature, which is their universality, feature that has been the key point for us to develop our approach to evaluate such correction via effective counterterms, approach that allows us also to compute this higher order correction with 3 topologies only. And if you include the theoretical uncertainty of the sub-subleading, you are, if you don't violate the Sudakov regime too much, as you have seen, you are able to preserve a percent level of accuracy, at least at this level of approximation. So our implementation has additional aspects. I didn't have the time to cover all of them, but if there are questions, of course, just please ask, and I will be happy to answer. And as David said yesterday, actually, there are problems in understanding how and when to perform the summation about these Sudakov logarithms. Is a point that everyone, I guess, should think about, everyone working on that. But I would rather to focus on the outlook, and the last point of the outlook, because due to this nature, if you are able to extend such approach to NNLO to loop, where of course computation are even worse in terms of time, you will be able to compute them via 3 topologies only, which of course will show even more the power of implementation. But the disclaimer is that one has to understand exactly how Sudakov logarithms behave at NNLO, since there could be huge cancellation among the one appearing at NLO and NNLO. And so that's all for me, and thanks for the attention.
Thank you for this nice presentation. Questions or comments to Lorenzo?
A very nice talk. Actually, we should have done the talk in the opposite order, because you explained much better the algorithm. So I want to ask you some question, which when you compare the NLO with the having or not these angular terms, that I think it's, yeah, I think there was some doubt.
So here, for example,
there was one case in which you said that it doesn't work, also including those terms. So this was
should be here because okay.
So what I don't understand, when you do this test, do you set put some cuts on the ZZ, or you are completely inclusive?
I think we have, no, let me check here. We should have just, I think we just have a cut on the PT of the Z in this process, but nothing on the invariant mass. Now it should be exactly at 100 GB. So we are not fully inclusive.
But in the one that is not
working, it has been obtained with the same run. So there is the same cut
Okay, that
for the
one.
Z boson.
Okay, maybe for that should be okay. No, because the thing that we observed that even including this additional term that if I understand correctly are the same one that
Yes,
we added.
exactly.
Okay, even including them, sometimes if you don't set cuts on the external particle, it doesn't work simply because you have some logs that appear that are not related to the virtual correction, but simply because also the kinematic that you have at the tree level can develop some log, I don't know, because the Z goes collinear
Yes.
to the beam, or in multiple, if you have more particle, two of them becomes collinear. So all these tests that we had showing that it works, we always had a separation angle
Okay.
minimum. Maybe for the case of the Z,
Maybe we should
it's
try it.
okay, but we always keep like a separation between the objects and cuts in the rapidity and minimum
I
PT,
see.
because otherwise it
See,
doesn't.
that's a good point. I think we can, since this is not the only observable for which, including the sub-subleading, there is no perfect match with the NLOVR result. There are other observables that I don't know if I have them in the backup maybe, or if I have just put very beautiful plots. Let me check. No, okay, that was the only case, but we have additional distributions, additional observables in which there is no full match. We can try to do something like that to check if imposing some cuts. That's a good point, actually. And so maybe that would reduce the uncertainty, because, as I said, we say that the not agreement is only due to the fact that we are not including box diagrams, which on contrary are included, of course, in the full NLO result. But maybe for some, maybe that's true. That's the only explanation. Maybe just including some cuts, as you said, we solve the solution. One can just use the standard code, and that's okay.
If I would like to ask the second question related to the same topic. So as you said, I mean, these additional logs, you don't have the full control over them because you may have some of them from the zero function, and so you cannot claim that you have the accuracy.
Exactly.
But counting them as uncertainty isn't too much aggressive. I mean, because you showed some distribution in which if you include them, it matches perfectly, and if you don't include them, it doesn't work. So treat them as a. So it may have like maybe.
Okay, I don't have a real answer, but what I can say is that maybe for those, I mean, we should maybe investigate this feature a little bit more, because it's not so trivial. But maybe, I don't know, if you include them, you just spoil again. So if the additional sub-subleading light terms coming from the box diagram are included, you spoil a little bit maybe the agreement, but that's okay because for some other reason, maybe due to cancellation, mass suppressed logarithms that we are neglecting, or order one maybe contribution can eventually be the actual responsible of the disagreement. I don't know. I mean, we thought, Jonas and I thought that would be the best, let's say, conservative way to say, okay, we don't have full control, just set it as an theoretical uncertainty, that if we include it, you get a perfect agreement in some cases. But yes, that's a good point. We should maybe investigate, as you said.
No, also because I mean, you include your idea is to include this term, maybe there is some summation to improve your accuracy. If then you count this term as an uncertainty, you may risk to have then at the end the uncertainty that is even larger from where you started. So it's maybe, okay to be, let's say, conservative, but it's not always the wisest choice.
Right.
I have a question in a similar direction. So, so with this Denner-Pozzorini formalism, you basically always factorize everything over the Born in a complete Born matrix element. But then, if you look at the full structure of the Sudakov enhanced logarithms, there are contributions then coming from what in a full calculation would be box diagrams, and in a factorized approach, you would associate this with some soft anomalous dimension. And then you have to take apart basically the Born matrix element in terms of its quantum number. So this is not what you're doing here, right?
No.
But this is then you're then not gaining full next to leading log accuracy in this approach, right? So then you're basically lacking some single logarithmic enhanced contributions there, which otherwise are present in the full calculation.
Well, this is not even a full calculation actually, because this
Yeah,
is for
I know,
virtual
I mean,
one,
this is,
just for virtual.
Right. I mean, but for electroweak, this is acceptable since you have a heavy gauge boson mass, but still there are classes of logarithms which you don't have in there.
And which kind of logs do you have?
It's basically from it's basically from soft exchange when a gauge boson becomes soft between any of these associated leptons there, and for that you would have to would really have to take apart the structure of the quantum numbers in the electroweak sector. So this is then not an overall factorization of the Born matrix element anymore.
What I think here, so definitely they are taking into account logs that factorize matrix element that have different final state than the one that you have at the Born, because I think is what he showed with these control terms. Because if you look how he writes the control terms, there is an index, so the matrix element that is appearing. Here, no,
No, it should be here.
This one, you see, when there is the V inserting there from one side of the other of the blob, there are different particles because it's an index.
Yes, of course. If you take the full,
Mm.
for example, let me take this one. Here, there are always indices.
So all the logs that are S over MW squared are correctly taken into account. The one that are not formally exactly taken into account are the one in yellow, because these are log between invariants, but the other are all okay.
And of course, when you then exchange, I mean, I'm not stressed it, but when you, of course, this is the Born matrix element always of the same process. If you exchange photon or Z bosons, if you exchange a W boson, this of course will be the corresponding SU2 flip Born matrix element.
So then this is give me like the assist to the
also,
next question.
These formulas are pictorial in the sense that I didn't put all the pieces, but we have additional logarithms taking into account ratios of different masses in case, in particular, of the presence of the top core or between the Z and W mass. We didn't do like in the Nerpozzarin that put everything in terms of the MW mass. Okay, we kept the masses as they are of the gauge bosons.
So another question that I have, so for example, in MATGraph, the problem that we had is exactly that since some of these log factorize a different matrix element, then when you look at the exactly not the correction to the amplitude, but the one that are entering for the cross section, you have to do the interference of an amplitude that have different final state and so different on-shell condition. What I don't understand, how do you deal with this problem? I don't understand if you have a smart solution to bypass it, or you still have to deal with some on-shell condition. So because we had to implement in our code the momentum reshuffling techniques, the one just to put on-shell the particle.
Well, in our approach, in the end of the day, what we have for, you mean for this kind of SU2 flip for, so when you exchange it, okay. Actually, with this counter-term insertion, the external states are always the same. What changes is basically these internal ones, okay? But when you interfere for the external states, that it's fine with the leading order, for example, they are exactly the same. this QQ, for example, what changes is here. And then you sum over all of them, of course.
No, but what I mean is that imagine that you are this blob is changing a W into a Z, let's say, okay, just or a top into a, even worse, let's say a top into a bottom. If the top is on shell, the bottom after the blob will not be on shell, right?
Yes.
Okay, so the algorithm is telling you that you should have a matrix element. You write it as logs times amplitudes. So this amplitude that you are considering in this case as the leg of shell.
Yes.
Is this a problem or?
Not actually in our code. We can always recast the. I mean, with our approach, as I said, we naturally have external states always to be the same of the process that you are studying. What is changing again is the internal one, but you don't really disentangle correction by matrix element as delta times m. For the sub-leading in particular, what we do is is to keep this correction. We don't factorize it exactly as we don't separate it in this way. Otherwise, yes, you would be right. You have a matrix element of different final states, and you cannot interfere with for example, the leading order. But in this way, we just compute we just compute it by default this full let's say NLO-like amplitude. I don't know if I'm not being clear. We can eventually, I can show you maybe later. Yes, it's quite technical with OpenLoops.
Okay, good. Then see no further questions, so we can take subsequent discussions offline. And let's thank Lorenzo again.